Good day, everyone. We are Karl Galapon, Francine Carlos, Johanna Vendiola, Keona Bocol, and Nathan Lim, led by Dr. Macario Cordel. And our study has the title of An Empirical Study on the Misprediction of Text Regions in Modeling Human Attention. So, salient stimuli attract visual attention and allow for completion of specific tasks. Significantly distinct elements called salient stimuli attract human visual attention and allow humans to concentrate on important information in a scene to accomplish specific tasks. This visual attention can be divided into two approaches. First is the bottom-up approach, which uses low-level visual attributes such as brightness, color, and texture in generating saliency. Next is the top-down approach, which uses high-level and context-dependent visual attributes such as the object of human action and gaze, familiar faces, and text information when it comes to generating saliency. In computer vision, researchers have been attempting to recreate human attention using neural network models. However, current saliency models do not consider human cognitive characteristics. They displayed excellent results in saliency benchmarking. However, these recent saliency models are non-inclusive of human cognition, such as recognizing information-dense text or simply informative text. As a result, predicted attention maps often mispredict the saliency of informative text in the image, as we can see in the figure. Misprediction of attention in an image is common in current saliency models. Particularly, the misprediction of attention in an image with text is common because previous studies on human attention prediction treated images as a whole instead of using bounded image regions. Thus, the objective of this research is to compare the attention of a human fixation maps on ground truth and the model predicted attention when it comes to text. For a recap of the efforts in this field, we look at the related literature. So the first study is Where Should Saliency Models Look Next by Bielinski et al. This study quantified the prediction error of current saliency models. Although the study has contributed to further development of saliency models, especially on the prediction of high-level concepts in images such as text, objects of gaze, and action, it lacked a deeper study on human attention prediction on informative text. The next study is a deeper look at human perception of images. This study identified factors that influence human perception. These factors include sentiment, memorability, and aesthetics. Furthermore, the computational models that predict high-level image attributes were designed. While this study focused on holistic cues, color information, and semantics of digital images, it did not cover informative text. And lastly, is the emotion-aware human attention prediction. This study provided insights on how different objects with varying semantics receive attention from an individual. This work focused on object sentiment and human attention, and it did not cover informative text. Now, let's move on to the methods. So the methodology is divided into 5 major parts. First is the gathering of images. We gathered 238 images and their corresponding fixation maps from the following datasets. First is the CAT 2000, and next is the object and semantic images and eye tracking or OC, and lastly is the emotional attention dataset or EMOD. So we established a few criteria for the picking of images. First is that image samples should have at least one text region that is legible and written in the English language. So here are samples of the images that we gathered, and we divided them into 2 different text region types. First is the informative text region. An informative text region is defined by at least 2 specific details that contribute to the context of an image. If the text region does not possess both those details, it is labeled as an non-informative text region. So the second step is the generation of predicted saliency map. First, we access a DLSU virtual machine with an Ubuntu 20.04 operating system. So here is the virtual machine with the Ubuntu operating system with the specific model. So the Ubuntu operating system is crucial for this step because we can install Cafe, a deep neural network, a software that helps run deep neural networks with one line of code, as shown in this slide. Next, we downloaded the Open Salicon from GitHub. So the Open Salicon, which will be the saliency prediction model in the study, is downloaded from its open source implementation, which is published on GitHub. Next, we wrote a Python code that loops through all the images. So for this step to be automated, we need an automatic code that cycles through all the files in a certain directory so that we don't have to manually calculate the saliency per image. So lastly, we incorporated the saliency calculation for the code such that when we run the code, all the saliency maps for all those images will be generated in one go. The next step is the creation of the bounding boxes. So it was said earlier that previous studies did not have a deeper look on human attention prediction of text because they did not have bounding boxes. So in this study, we will be using the bounding boxes. So the software label ing was used to create bounding boxes, which we then exported as an XML file. So when it comes to creating the bounding boxes, we identified four important groups. First is the PINF, informative text regions from images containing only informative text. The CINF are informative text regions coming from images with both informative and non-informative text. The PNNF are non-informative text regions from images containing only non-informative text, and the CNNF are non-informative text regions from images containing both informative and non-informative text. So for the last two steps, we generate the text region masks and calculate the attention scores. So first, the bounding box coordinates were extracted from the XML files, which were exported from the label IMG software. So what we can see here is a sample image and its corresponding XML file that states the coordinates of the bounding box. Additionally, we can also determine the dimension of the image using the XML file. So given the coordinates, we can draw a white rectangle on an all-zero array with the size of the image. So it will look like something like this. Here we can see a white rectangle drawn from the coordinates of the bounding box on an all-zero array, which is a black image that has the same size as the original image. Next, using the OpenCV library, the fixation maps were multiplied with their masks. So what does this do? This is essentially the masking process. So here we have the mask, and we multiply it to the fixation map of the image that I've shown earlier, and it will result in isolating the fixations on the region that we want to mask. So why does this happen? So we remember that the rectangle has a value of all 1. So when we multiply it to its corresponding location on the fixation map, it will simply duplicate that region in the result. And everywhere else outside the rectangle, which is a value of 0, it will turn the values in the fixation map into 0, resulting in a black color. Lastly, the maximum value or AS per region was obtained. So using the numpy max value command, we can determine the maximum pixel value in the mask fixation map. And usually those range from 0 to 255. So in order for us to obtain a normalized range of 0 to 1, we divide it by the maximum value, which is 255. So 229, which is the maximum pixel value here, divided by 255, results in an AS of 0.898. So lastly, of course, this process is done for both fixation maps or ground truth and saliency predictions so that we can compare them statistically. Now, we move on to the results and discussions. Here we can see the descriptive statistics for the calculated AS of both ground truth attention maps and prediction attention maps. So first, we can observe that the ground truth AS of both informative text and non-informative text regions both decrease when they co-occur. As we can see, the PINF goes from 0.75 to 0.69, and the PNNF goes to 0.57 to 0.45 when co-occurrence happens. Next, we can observe that the differences delta P and delta C between informative and non-informative text increase when they co-occur. So, what are delta P and delta C? Delta P is the difference between PINF and PNNF, whereas delta C is the difference between CINF and CNNF. So, we can see from the ground truth group that the delta P increases from 0.18 to a delta C of 0.24. And for the predicted group, the delta P of 0.09 increases to a delta C of 0.16 when co-occurrence is present. So what do both of these results imply? Both suggest a competition between the two text region types when they co-occur, with informative text having generally higher AS. So we can see that the AS of the informative text groups always have a higher AS than the non-informative text groups. Next, we can observe that the ground truth and predicted PINF have a larger difference compared to the ground truth and predicted CINF. We can see here from the PINF column that the ground truth PINF 0.75 has a difference of 0.9 to the predicted PINF, whereas the ground truth CINF has a difference of 0.01 to the predicted CINF. So what does this result say? This suggests that mispredictions in informative text may only occur in images where they do not coexist with non-informative text. Now, let's look at the distribution of high AS and low AS. High AS are attention scores that have values of 0.5 or more. So we can see here that the prediction model determines the location of informative text because, as we can see from the histogram, it distinguishes high AS from low AS, which is analogous to saying it distinguishes from informative to non-informative text. However, it may have the capability to distinguish informative from non-informative text, but it still lacks the capability of an accurate prediction of the attention scores. Lastly, we do hypothesis testing on the groups. So we can see here that for all the AS of the all groups within ground truth and predicted, there exists a significant difference between informative and non-informative text. Thus, generally, informative text AS is greater than non-informative text AS with more than 99% confidence. So, now we arrive at the conclusions. To summarize everything, we utilize Salicon to generate predicted saliency maps through a virtual machine with the Ubuntu OS. The predicted attention in text regions is compared by conducting hypothesis testing. Then the difference in the attention scores is analyzed with descriptive statistics in which data was extracted from the ground truth and predicted attention maps for all types of text. With these steps, findings show that the attention score of both non-informative text and informative text decreases when they co-occur in an image. Human attention is also greater when images contain only informative text. And lastly, informative text regions are generally more salient, whether solely existing or co-occurring with non-informative text in an image. This brings us to the end of our presentation, and thank you for listening.